Yes. It's not here yet.
Power comes responsibility.
Okay.
So we have to change the camera. So this is now the first camera.
Okay.
Once the speaker goes to the second camera, all you have to do is just press on this. And then it goes to the second camera.
So, and then left camera.
We want.
You're the first camera.
They took out the because of the camera. See, that's thank you.
Okay.
I mean, hopefully a few years ago.
Yes.
Exactly.
The precious one.
It's like one tiny bit of Hagoromo. I don't know if it's enough for the talk, but
No, but you have another one here. Maybe this is use with care.
I will try to write as little as possible.
Okay, welcome to the afternoon session. Our first speaker is Eduardo Silva, who will speak about non-universality of boundaries of amenable groups. Please, Eduardo.
Thank you very much. Yeah, so I would like to first thank the organizers for giving me the opportunity to speak here, and also the rest of the speakers, because this conference so far has been very nice. I really enjoyed the talks. So yeah, I mean, I guess we've heard a lot about boundaries of groups during the week, in many different senses, right? Maybe the most, the one that has appeared the most is the Furstenberg boundary, right? We have characterization of system simplicity there. Now I'm going to speak about boundaries from a measurable point of view. Here we have advantages and disadvantages. We'll speak a bit about them. But I will also speak about interplay with topology. Okay, so what's the interplay between this measurable version of boundaries and topological version of boundaries, and what one can expect, what one cannot expect, depending on the geometric properties of your group. So it's very nice that I'm speaking after Yair, even if he's not here today, because he did some introduction to motivation for studying probabilistic boundaries of groups and spaces of harmonic functions. So the main object today, well, maybe first some context. So G for me will always be a countable group, and so I'm going to start with some definitions. So I'm also going to fix some probability measure on G, and just to avoid giving too many details or too many conditions, I will assume directly that it's non-degenerate. So its support generates a group as a semigroup. By the way, at any moment, if I say something that's not clear or they don't write and want me to do it, just tell me. Anyway, so start here is the Poisson boundary. Yesterday, I called it Poisson-Fürsteiner boundary. You can also do that. I call it Poisson, just to read a bit less. So this is a probability space. I will call it just B nu, on which G acts by measurable transformations. This is not a measure preserving action, but it's rather a stationary action. What does this mean? It means that nu can be recovered from averaging nu according to mu. Yeah, so stationary. And most important property, well, this space is unique up to isomorphism, and most important property, you have representation of bounded harmonic functions, right? So you can read in an infinity of B, so in this boundary here, bounded harmonic functions of group. So not only will we be interested on the Poisson boundary, which is this universal object that satisfies this correspondence with harmonic functions, but we will be a bit less ambitious. We will care about boundaries in general, so maybe potentially smaller spaces, but which still capture some, from one point of view, asymptotic information of the group, or from other points of view, harmonic functions. Okay. So I will define what it means to be a mu boundary. Okay, so this is the most, from my point of view, the most reasonable way that one could define a probabilistic boundary for the group. For that, I will very briefly recall what a random walk is. So I guess Jair was also saying yesterday you can think this from probabilistic point of view or from more ergodic theory point of view. So for me, the ergodic theory point of view is that you just look at sequences of G, and you endow this with Bernoulli measure. Is a space of increments. So same as Jair yesterday, this is G1, G2, G3, etc. Increments. And we're going to form the random walk, so we're going to start doing partial multiplication of the increments. So we also get sequences, but now it will be G1, G1, G2, G1, G2, G3, and so on. So this I will often call W and N. And again, by definition, the law here, I'm calling it P mu. Yeah? So this is my space of trajectories. Okay. So what is a mu boundary? So a probability space, let's say G space. So here, G space just means that G acts by measurable transformations. We say that it's a mu boundary if there is a way of associating two paths points in the space, of course in a measurable way, also in a G equivariant way. So if I do random walk and I do random walk and I reach a point, or if I start at G and I reach a point, then I will reach G, that point. Yeah, so that's what equivariance means. You're also wanting to depend only on the tail of your random walk, so you're going to ask it to be shift invariant. And of course we want to understand the measure, so we want this lambda to be the push forward of the random walk. So such that lambda is pi star p mu. Okay, so this is a new boundary. And in this sense, one way to define the Poisson boundary, I don't know, maybe you read here, is as a maximal mu boundary. Yeah, meaning that any space with these properties will be a G equivariant factor of it. Okay, so this is a definition. I hope everybody agrees that this, I mean, if you've never seen this before, this is a very reasonable way to call something a boundary. You just want things that are invariant, so they depend only on what you do at infinity. You want to have G equivariance, that's all. And yeah, so by studying these objects, you can understand lots of properties from your group. For example, you can understand amenability. So for that and for what I will, amenability is part of that also, I will speak a bit about that. A particularly interesting class of measures are what one calls Liouville measures. So the measure mu is called Liouville if the space of bounded harmonic functions is just constants, which in terms of Poisson boundary is the same as saying that Poisson boundary of G mu is trivial. Yeah. And the theorem, I will state that because it's one of my favorite theorems, due to Rosenblatt and independently by Kamanovich-Vershik. Sure, everybody is familiar. G is amenable if and only if you can find some probability measure on G, non-degenerate, and Liouville. Okay. So here we already see that a very concrete geometric property of the group is detected by the random walks or these boundaries, right? This is the same as saying that this measure has no non-trivial boundary. In general, there's a comment for things that will maybe come later. This measure, you cannot choose it to have, for example, finite support. In general, it will be necessary that it's very spread out. So there are groups for which no nice measure has this property despite them being amenable. Okay. Okay, and before getting into the main question that I want to address today, I will also do some motivation, which is also this other theorem, much more recent, maybe, how much is it, 40 years after, I guess? I don't know. Which is why would you like to study these type of spaces, also related to the topics of this conference. And it's this very nice result, very impressive result of the two people that are not here, so Hartman and Kalenter. So please someone text them or something that I'm citing them. A few years ago, I guess it was published on 23, but it was in the archive earlier, which is precisely this measurable version of this characterization of, well, Caesar simplicity, not with the first order boundary, but now rather with stationary spaces in which a group acts, and in particular with new boundaries. So I will state it like this. So I will do two statements. So the first one is that if G is Caesar simple, then you can find a probability measure on G such that G acting on its Poisson boundary is essentially free. Yeah, so that makes sense. And I guess you can read here now that there's no TV. So I will write there. So now the other way around. Suppose there is some probability measure on G such that, I'll continue here, there is an essentially free new boundary with, I will explain this, a compact model, not only compact but also uniquely stationary, stationary model, then G is a simple. Yeah, so just as since the simplicity implies that your action on the first boundary is essentially free, we have the first statement, now in the measurable setting. And the other way around, if you're able to find some probabilistic boundary with two conditions, you have an essentially free action, and this is maybe proper to this setting, you want to be able to realize this probability space with a compact space, and not only compact, but also that it has a unique stationary measure. So remember, this compactness argument that Yair explained yesterday always guarantees the existence of stationary measures. In principle, there will be many of them. There you're asking that there is a unique one. So it's like the stationary equivalent of unique ergodicity. In that case, you're able to guarantee sister simplicity. Okay. The advantage... Yes, exactly. It's a measurable version of Bayard, Karantarosawa, Kennedy. Yeah. And the advantage of this is that, yeah, I guess maybe you know this better than me, but like, first time boundary is not easy to look at, right? I mean, it's a very not well-behaved topological space. Whereas this, like in practice, you're able to see that in many examples, you're able to find these spaces rather easily and show unique stationary rather easily. So this gives you a more concrete, hands-on way of verifying sister simplicity, at least in abstract. So I will not speak about sister simplicity today, but this is a motivation. Maybe I do have projects on that topic, but not today. Maybe some other conference. I want to order a bit stuff, so I'm going to do a definition here. So I want to understand this interplay precisely between measurable boundary and topological models. So let's say the following. We will say that if your group G acts by homomorphisms on a, for the moment, let's just say Hausdorff topological space, we will call X a morphification of G if it has the following properties. You can find a subset X0 of X. You can think of this subset as just being 1 point for the definition, but in general it will be a subset that is minimal. Minimal in X0, so every orbit of X0 is dense there. Such that for all probability measures on G.
So G invariant.
Yeah, yeah. Yeah, it's contained there, yeah. For all probability measures on G, non-degenerate of course, you can find some base point in X0, so little X0, such that when you push X0 through the random walk, this converges almost surely. So the limit as n goes to infinity in X is mu almost surely. Yeah, so I repeat, what does it mean to be a modification? So there are like 4 or 5 lines there, but it's very simple. You just want to have some space at infinity such that, well, maybe X is all of it, and then there's some X0 here. And for every step distribution that you choose, you want to be able to find some base point X0 such that this will almost surely converge at infinity. We will see some examples, but before, I mean, most of what I will explain will be very concrete examples, so everything will be clear. But before that, maybe a quick remark. So, of course, if we have this, if you go back to what I just erased, in this case, the space X defines a new boundary with a probability measure which will just be the distribution of this limit. Okay? Yeah, you just define the map pi from G to the Z plus to X, such that at each sequence you assign the limit of W and X naught. Okay? And this is the heating measure on X. Yeah, so I hope that is clear. So first, what happens if we were to have a portification and our measure mu is trivial? So measure trivial means you have no asymptotic behavior, your Poisson boundary is trivial. So if this measure were not to be trivial, this would be a contradiction, right? So if mu is trivial, then this heating measure has to be a point mass. Yeah, your random walk converges, so it has to converge to always to the same point. Otherwise, you will have asymptotic events that would lead to non-constant bounded harmonic functions. Okay, and moreover, so this is, I mean, up to this point, this is.
Follow the quantifiers. X0, big one, does not depend on mu.
Precisely. So x0 is, yeah. So for each measure, you find a base point, but the space of base points is minimal, independently of measures. Yes. So again, for the moment, if you want to simplify things, just suppose that x0 is just a point, and most of the cases will fall there. This is just to make it a bit more general. That will cover more examples. Are there any more questions? Just interrupt me if there are more. So what I was saying is that up to this definition is not the best, because you could just take X to be a point, right? And it will satisfy this definition. A one-point space is a modification for me. So of course, I do not want that. I want modifications to be interesting. So I will define other concept. So call modification X. So I'm not very creative. So I will just call it good if the following holds. Whenever you have a measure mu that is not trivial, then the heating measure is not a point mass. It's not delta. Okay, so I'm saying it may happen that my heating measures are concentrated on a point, but I want this to happen only when there is no other possibility. So if my measure admits non-trivial Poisson boundary, or only non-trivial asymptotic behavior, I want my modification to witness it. Okay, so I hope you agree this is reasonable. And we will work with this the rest of the talk.
Why don't you call it non-trivial?
Because, I mean, it could be that for some measures you detect non-trivial behavior, but for some of them things collapse. So it's not really that it's trivial, right? It's trivial sounds like it's a once. It's like it collapses everything. So I don't know. By the way, if you have any other name recommendations instead of modification, I also accept them because I really do not like that word, and there are like so many things called boards or boundaries or stuff like. So please, like, send me an email or something. Anyway, so let's see some examples. We good? So what's going to be my first example? A free group, right? Yeah, okay. So, so what happens if you have a free group? Then I guess this is usually attributed to Furstenberg in the 60s. that in this case the geometric boundary of the free group in my notation is a good modification. And it's a good modification with x not just a point, right? So whenever you have any random walk on the free group, as long as it's non-degenerate, it's going to converge almost surely to the boundary, and this heating measure will be non-atomic. So I guess Furstenberg did kind of prove this for matrices. I don't think he actually stated it for free groups. If you try to find this precise statement in the literature, I think the earliest you can get is Kajmanovic-Verchik in 83 that...
It is Dembkin and Maluto.
No, but I don't think they prove it for any probability measure. I think they prove it for finitely supported random walks. Dembkin-Malyutov. I think, yeah, so Dembkin-Malyutov definitely proved it for finitely supported, but this is...
They were describing Martin boundary, so they were not just interested. Is it more difficult to generalize?
Yes, it's not the same argument that they do. You need to use martingale convergence theorem for this, and I don't think they do it that way. You need martingale convergence theorem. But anyway, so I was saying this is in Kajmanovic-Verchik, but it's not proof there. It's just referred to, the citation is just oral communication by Margulis. That's like the earliest citation of this statement that you can find, which I would think it's funny. And maybe for some, well, there has been a lot of work in the past years around just this topic, just free group and boundaries there. And actually, in many cases, you can actually prove that this is the Poisson boundary. So this is the maximal space. So this is Kunal Chawla, Josh Frisch, maybe I did it the other way around, Bernard Forgani, and Giulio Tiozzo, who showed that with one extra assumption, if you have finite entropy in your measure, so this is Shannon entropy, so sum over G, mu of G, log mu of G, then this is the Poisson boundary. This follows work a lot of many people. The best result before this was Kajmanovic, like 20 years before this. But what is extremely surprising, which was a breakthrough last year, was by the first two authors, so Chawla and Frisch. So this was last year. This is not necessarily true if you are in the infinite entropy regime. So they are able to construct probability measures that are non-degenerate on the free group, and for which the Poisson boundary is strictly larger than the geometric boundary, which was super surprising. I don't think people expected that to be the case. Right? You have your free group, you're doing some random walk here. Okay, you're doing very long jumps, but you're still doing a random walk here. And somehow you manage to get more randomness, more asymptotic behavior than the one you see in the drawing at infinity. So this is super interesting. Yeah, and maybe for this example, of course, you can guess that this generalizes to acylindrically hyperbolic groups. Also to lattices in semi-simple Lie groups. Okay, so many examples are very similar.
So in these constructions, I mean, do you also get some geometric interpretation of what's outside of the...
In the examples they construct, you do, but their theorem is actually like the best thing you can hope for, in the sense that they really show whenever you have any ICC group, any reasonable group, and any probability measure there, you can always get to another probability measure such that the Poisson boundary is strictly larger. So you can always like go up and up and up and up. So yeah, in their precise examples you can find some geometric interpretation, but yeah. Someone is interested, we can speak about that later. It's a very fun construction. Okay, another class of groups that I wanted to mention are groups acting on the circle. So take, so if you're interested on one manifolds, you may want to understand group of orientation preserving homomorphisms of the circle. To make this non-amenable, let's say that the action is minimal and proximal. So proximal just means that you push points together through group elements. So basically, if you have two choices, you can choose this. Either your group fixes a probability measure on the circle, in which case it will be basically rotations, or up to an extension or something, it will be of this type. So this is really a generic situation. Then in this setting, it's a theorem of Bertrand de Juan, Klepsin, and Andrés Navas, almost 20 years ago. Sorry, 07. That here, the circle itself is a good boundary. Sorry, modification. So what this hypothesis implies that when you do any random walk, points in your circle are going to, well, your random walk is going to choose some limit point in the circle, and things will start getting contracted towards this point. Yeah. So this will define a unique stationary measure on your circle. So all of these examples I've spoken so far are uniquely stationary, and this will be a non-trivial new boundary. Of course, in some cases that will be the Poisson boundary. For example, if you have like a compact lattice on SL2R or something, like something that acts on the hyperbolic plane. But maybe I want to highlight very quickly a result of mine and some collaborators, which I think is very fun. That's why I included it. So this is with, who are they? Martin Dillaberrio and Cosmas Kradaris and me, which is that if you further suppose that the action on the circle is topologically non-free, meaning that you have, so you're really not in the situation of groups acting in a hyperbolic space. You have intervals on the circle that are fixed by group elements. Yeah, that's what being topologically non-free means. And again, finite entropy assumption. Then the circle is never your Poisson boundary. So it's kind of fun. You have the same hypothesis of finite entropy, but to conclude the exact opposite statement. And the reason is, intuitively, it's very simple. It's just that the circle is too small. You're converging towards a point in the boundary, but there is so much randomness. There's so much randomness happening here that is not being captured by this boundary point, and you can formalize these ideas. What I think is very cute about this result is that it applies for Thomson's group T. Thomson's group T is dyadic, piecewise dyadic transformations of the circle. And when you think a while about this theorem for this group, this statement just has to be true, and the reason is that if you were able to prove the negation of our theorem, so if you were able to find some probability measure in T such that the circle is the Poisson boundary, then you would have proved that F is amenable. Okay? And why is that? It's because general theory tells you that a group acting on Poisson boundary, the action is amenable. So stabilizers will be amenable, and F is contained on the stabilizers of this action. So if the opposite were true, then we would have proved that F is amenable. So this is the maybe not so interesting version of that theorem. Okay. Okay. So now, final example, and of course my favorite, are Greek products. And here we finally land on the amenable side of things. So three Greek products. Yeah, so I guess most people are familiar with the construction, so I will not spend too much time saying that. If there are questions, please let me know. But you have two groups, A and B. The grid product, yeah, I guess you have to choose the order in which you do it. You take my notation, direct sum of copies of the first group, so you call this the group of lamps, and you take an extension by the second group, where the action here is just by translating the indices. Okay, so you think of this as Lamplighter groups, so your group elements are lamp configurations together with some position, and multiplying by group elements corresponds to moving this position around and changing the lamps in that neighborhood. So when you look at the random walk, Wn, you are able to express it as a pair, right? Fn, Xn. So this, just to be clear, this will be lamps, and this will be position. And something that happens often, and that was first noticed by Kamenowicz and Vershik in their paper, is that in many situations, the lamp configuration stabilizes. And what do I mean by this? For every element in the base group, almost surely there will exist an instant such that beyond that instant, the value of the lamp configuration at this position does not change anymore. Okay, so yeah, you really have to imagine that you have your V here, and you have your person moving around and lighting and modifying lamps. And in many situations, so this will be in particular if, say, mu has finite support, and the projection to the base group is transient, so you go to infinity. So just think of this situation. You're going to be modifying lamps somewhere over here, but this person is going to infinity. So when you look at any given finite region of your group, there will be a moment after which the person left and never came back, and then the lamps there will not change in the future. So this is what's happening in many situations. And in this setting, if this holds, then the space of limit lamp configurations, so this will be something like product of A over B, so now a real product, not a direct sum, with heating measure, is a boundary. Yeah, and historically, I mean, just to mention, this was the first examples of amenable groups that admit non-trivial boson boundary, given, well, maybe for symmetric measures, given by Kamenowicz and Vershik. So maybe I will also mention, so I've been speaking about boson boundaries all the time, so I will mention, is this a boson boundary or not, right? So this is a theorem that has been studied by quite some people. Most important contributions are by Anna Eschler in 11, then by Russ Lyons and Yuval Perez a few years ago, and then by Josh and I in my PhD. Yes. Which is that, so just to simplify statements, let's say that G is A with ZD. So I'm fixing what the base group is to be ZD. In any case, we're interested in amenable groups. This is a large class of amenable groups. So suppose, again, finite entropy, and suppose that we are in this condition. So let's suppose directly that you have stabilization. Then this place is the boson boundary. So the previous references they do not directly assume these type of things. They rather assume, for example, finite support or finite first moment or other things. Our contribution with Josh for this was to directly assume that you have a well-defined boundary. Yes, it's more like a qualitative hypothesis. Suppose that this space is well-defined, then this is the Poisson boundary. So, for Josh and I, we were super happy with this, but this was also somewhat frustrating, right, if you compare to the previous examples. And why? Because we have this hypothesis here. One would like to be able to describe the boundary or be able to understand this boundary behavior all the time. Maybe even not the whole Poisson boundary, but again, just a good portification. There will be measures for which this thing will not stabilize, and for those measures, nobody has any idea to how to construct a space, a compact space, for example, on which your group acts and such that random walk stabilizes. But in principle, there could be such a space, right? You could think that ideally for any probability measure, maybe you could define some very complicated functional in terms of growing and growing neighborhoods or something, in terms of the lamps or something. So you could define a very complicated space that does have this property that identifies boundary behavior, right? So we were frustrated that we couldn't find it. And the main theorem that I want to speak now is explaining that that type of things really cannot be done, okay? So the amenable realm is really very different than the rest. So let's take that here. So this is work, as I said many times, this is work in preparation with Josh Frisch and me. So yes, this was proved during Damian Gaborio's birthday conference. Some of you were there, yes. Take G an amenable group. And we're going to suppose also that it's ICC. Right, so every non-trivial element has an infinite conjugacy class. If this is not the case, basically you are, well, up to so finite index, you are in the case where you are virtually impotent or hyper-central. So there doesn't really make sense to speak about boundary behavior. So this is really not a hypothesis. Let X be a modification of G. Yeah, in a previous sense, so remember a topological space such that all random walks converge with some base point, H. Then you can find a probability measure on G. That's going to be non-degenerate, symmetric, and you can also choose it with finite entropy. So compared with the other statement of Josh and Kunal Chawla, where their measures necessarily have infinite entropy, with the following properties. So maybe I will write here such that. First, the action of G on its Poisson boundary is essentially free. So in particular, the Poisson boundary will be non-trivial. And nonetheless, the heating measure is a point mass. So yeah, a delta function. So I will explain. So remember, free groups, hyperbolic groups, lattice and semi-symbolic groups. There was also this, always this geometric space at infinity with the property that random walks converge there, and that you're always able to identify your non-trivial boundary behavior there, even for the circle, right? For the circle, this theorem says it's not the Poisson boundary, but okay, let's not be that ambitious. It's still a space on which a group acts and which detects very fairly boundary behavior for all measures. Maybe not all boundary behavior, but it detects all of it. Our main theorem says that in the amenable setting. Yes.
So what is?
Nu mu is the heating measure. Yeah. So this is
X.
on X. Yeah. Are there more questions? Yeah, so as I was saying, our theorem is saying that for amenable groups, there's absolutely no hope of finding such a geometric space, even if you are very clever and you do a very complicated construction. Whenever you're able to trap your group inside some space such that random walks converge, there will be some measures that spit out and which trivialize their boundary behavior, even though they do have non-trivial boundary behavior, right? So that's how you should think about this theorem. So I give you 1 minute to reread. I know it's a bit technical, but I hope the ideas are clear. Yeah, as I was saying, for many applications, it's sometimes useful to have spaces that realize simultaneously boundary behavior, or that realize simultaneously Poisson boundary, with a same X for many different mu. So this tells you that you're in no good place for amenable setting, and yeah, anyways. So in the last few minutes I just want to give very little ideas on how you prove this kind of result. Yeah, it's very general, right? How do you approach this? And yeah, so it's kind of funny what Yair was saying yesterday, that you have this like two schools, like 2 points of view. Either you are from a very probabilistic background and you do hard probability, martingales, etc., or you are from more like ergodic theory and PMP actions, and you do some maybe more abstract group action, and then you conclude things. So this is a statement about group actions, right? However, the proof we do is very probabilistic. So it's again the two worlds having an interplay. So the proof, I will explain some technical lemma, but which will make sense. Which I call the coupling lemma, which is going to be, as its name says, a probabilistic coupling between some random walk with non-trivial boundary, which will be mu, with alluvial random walk, which will have trivial Poisson boundary. So I will write while I explain. So you will start with some alluvial measure. So they exist because your group is amenable. And there's the statement. So then there are, and, okay, get ready. So first, eta, probability measure on paths. Probability measure on paths. A probability space, abstract probability space, omega, with a measure I call gamma, and random variables. So measurable functions, w and w tilde from omega to paths with the following properties. So the first is that this is a coupling between eta and mu0, meaning that when you look at the law of w, you see eta. Okay, so when you project to one coordinate, you see eta, and when you project to the other coordinate, you see the alluvial random walk. Yeah, so coupling part.
are.
It's a push forward of the probability measure of my abstract probability space to paths. So you have to think of this as a random walk, some distribution. Both of these are distributions on paths. Yeah.
Why are you acting from the right?
Yeah, just written it this way.
I'm acting from the right. What?
Do you mean W lower star of gamma?
Yes. Yeah. Sorry, it's a long talk. Yeah. W star of gamma. Yeah. Sorry. Thanks for correcting that. Thanks for paying attention. There it's okay. Yeah. Yeah. Of course, you're pushing the law through the random variable. Yes. Anyways, so you have a coupling, and this coupling satisfies that for gamma, almost every little omega. So I try to make it round to distinguish from the from the random variables. There will exist sequences mi going to infinity, such that w of omega ni is equal to w tilde omega mi for all I. So the second condition is saying that for my two random variables, even though they have these marginals, so one marginal is this eta that I have not explained, and the other marginal is Liouville random walk, they trace each other. So I can, when I see W and when I see W prime, there will be infinitely many moments where they take the same values in the group. Okay? This is what this is saying. And finally, número 3, there is lambda. Okay, so this is the most fun part for me. It's a probability measure, but it's actually a probability measure on the space of probability measures of G, such that this mysterious measure eta disintegrates as a random walk according to lambda. Okay. And such that all of these measures are have the hypothesis there, the conclusion there, essentially free action on the boson boundary. So such that lambda, almost every mu, has finite entropy, and the action on the boson boundary is essentially free. Okay, so I will re-explain. This is the whole technical lemma, which takes a whole board, apparently. So what we're saying is that I'm saying that I'm not able to show you a single explicit mu that satisfies our theorem, but I can show you a generic one. And the generic one will be sampled according to this measure lambda. So what I'm saying is that, that there is a way of sampling distributions in your group such that when you first sample lambda and then you run a random walk, this is how you sample in the space of paths. You can do this in such a way that you trace a Liouville random walk, and such that nonetheless your boson boundary is trivial. And if you're willing to believe this lemma, then the conclusion of here follows immediately, right? Because if you were to have a modification, then you would have your x naught that through one random walk converges, but also through the Liouville one converges, but they intersect each other infinitely often, right? So they have to converge to the same point. But then this implies that since the Liouville one has delta mass as a heating measure, the non-Liouville one must also necessarily have this delta mass as heating measure. Okay, I will stop there. Thank you.
Are there any questions or comments?
Yeah.
Very interesting talk. So I have two questions. First is, do you have any examples where, for example, you can say that maybe some classes that lambda is a point mass?
No. I mean,
You know that it's always not a point mass, or?
I mean, from our construction will always be not a point mass. I don't know if, probably, our construction will always not be a point mass. Yeah. So,
can you, for example, say that it will be concentrated on some subset of bad measures?
no. So maybe that gives me an excuse to explain a bit how lambda is constructed.
Yeah.
So so this will not be very long, hopefully. So basically, lambda you construct in 2 steps. So I put the explanation here. So you're going to profit from the fact that mu0 is Liouville, right? So what does it mean for mu0 to be Liouville? It means that its convolution powers, its supports will basically be Fellner sets, or will be concentrated on Fellner sets. So you have here mu0 star and I for some ni, not the same ones, for a sequence that grows very large. And what you're going to do, first, step 1 is to sample elements. So these elements will be, I don't know, gi according to these powers. And then you're going to find some probability measure p on positive integers that has a slow tail. So it's very likely to give you large values. And you're going to define mu as p of I delta gi. So first you flip a coin with infinitely many values, and according to that value you choose a very large Fellner set that works you. Yeah, so this would be like d lambda of mu. Yeah. So you can see from this construction that it's really not a point mass. It's really quite the opposite. You have a way of sampling group elements in a random way, independently according to very large Fellner sets, and then you leave them aside. So I have this element from the first Fellner set, this element from the second Fellner set, G1, G2, G100, and then you start flipping coins with the measure P, and okay, first I got 25, so then my W1 will be, okay, 25, so it's G25, then W2 will be G25, and then I sample again and I get, I don't know, G6, and then I multiply like this. And this will be my random one. Yeah.
If there is question, let it be a question first.
Please go.
So maybe I missed it when you were talking about that. So in your paper with Martin and Cosmos, did you manage to construct explicitly some larger boundary than the circle? And is it kind of a general method that allows to do that?
So in this other paper, so for the theorem I stated, for a general group acting on the circle with a non-topologically free one, we do not have a different boundary. It's an entropy argument. So yeah, we do not know how to construct a boundary there. But in many situations, and in particular for Thomson's group T, you can construct another boundary. Which, yeah, I mean, it goes back to an idea of Kajmanovic, which is that when you look at F, your group is going to look like this, right? And, well, on T is going to be the same, except that these two things are glued together. And what's going to happen is that these derivatives here are going to stabilize at infinity. So you can show that something similar happens for T. And you can show that this gives you a different boundary, but we cannot prove, and we do not know if it's like strictly larger than the circle. So it could be that they share some harmonic functions, but it's by no means clear, and I personally don't know if it's true that anything that you can obtain from the circle is contained there or the other way around.
You cannot prove that that is not Poisson boundary.
I cannot prove that that is Poisson boundary, and I also cannot prove that that together with the circle is not Poisson boundary, which would be the easiest sounding statement that you want to show. Yes.
Yeah, my remark is the following. You mentioned the name of Rosenblatt, Joseph Rosenblatt, some article of 82. He has article 1972-74 with title something like Invariant Measures and Growth Conditions, where he introduced notion of supra-amenable group. So amenability play important role. Yesterday was colloquial talk on that. So supra-amenable strong condition and it's now almost forgotten. Despite that Rotterdam, I think, has some articles that uses this. Here I have two questions. So if a group contains three sub-semigroup and two generators, it is not supra-amenable. So two questions: is it correct that a group is supra-amenable if and only if it doesn't contain three sub-semigroup and two generators? First question. Second, if there is supra-amenable group of exponential growth. And I answered on the first question in negative way, but the second question still is open. There is no problem session, unfortunately.
Maybe at the dinner.
You are welcome to come next week. And then there is a problem session.
Any time is good for asking good questions. So, any more questions, comments?
Do you know anything about the expected growth of this sequence NI?
Yes, you can to some extent control it. Yeah, so it's very much related to this probability measure P you choose here. So I don't know if to speak about this, but okay, so it's not so difficult. So this measure P, if you're familiar with the construction of Hartmann, Frisch, Tamuz, Vahidi, Fedosky, you make it to have eventually simple record times, right? Which means that you want to take an independent sequence, and you want the maximum to be simple for values large enough. Yeah, so you want when you do a maximum, maybe then you do something there, but then the next maximum is larger, it's not equal. So basically these NI's are these times, are the record times of the sequence, and you can really understand what they look like, depending on P. Yeah.
Okay. Let us thank our speaker again. And now we have coffee break.